So look at the late season droughts, which are subseasonal, so they almost like extreme events, not flash droughts in that sense, but we will talk about flash droughts later on in this series. So here we are looking at a paper from Venugopal, as I mentioned in the last podcast. It's trying to look at non-El Nino droughts. If you look at the excess years and deficit years in the monsoon, we already mentioned before that only about 50% of the drought years are explained by El Nino, and only about 50% of the wet years are explained by La Nina. So what causes the non-El Nino droughts, and how are they different from the El Nino droughts? The paper focuses on that. So we start by looking at these El Nino droughts and the associated sea surface temperature pattern. You clearly see the El Nino warming and the horseshoe pattern of cooling here, with a kind of a IOD-like pattern here, which again raises questions about exactly what IOD is and whether it's independent of El Nino. And I will record this in maybe a course on El Nino, or a short course on El Nino. The non-El Nino droughts have a different SST pattern. The signature is not so strong on the equator. It's the ITCZ signal here, and it has some coldish pattern over the Indian region, and this here is identifying the El Nino droughts in red and non-El Nino droughts in blue. And you can see that overall the El Nino droughts are stronger, or they have a larger deficit in rainfall. These are rainfall anomalies for the season around the long-term mean, and we are looking at more than a standard deviation here. So what happens if you look at the evolution of these El Nino and non-El Nino droughts? They are remarkably different. So El Nino drought starts with a deficit and keeps growing into the season. So you're starting here on June and looking at days here. So you can see that the El Nino drought produces a deficit in the peak months of the monsoon, July, August, and then seems to recover a little bit, even though the deficit is still not greatly positive in terms of anomalies, daily rainfall anomalies, and then it goes negative again. Whereas the non-El Nino drought starts even more in a composite, with a limited number of El Nino and non-El Nino droughts in the whole century that is looked at here. But sampling is always an issue for many of these El Nino and monsoon studies. You cannot do much about it. Nonetheless, starts with a deficit that seems greater than the El Nino drought in the early part of the season, and then it seems to recover. So it's actually got positive rainfall anomalies during part of July into August, and then it crashes. So there is a late August, September break period that is appearing, and that creates a drought that's essentially of subseasonal character, because it's happening here in part of this season, the late season, which reminds you of the last podcast where we were looking at late season extreme rainfall, extreme wet years, right? So if you look at the evolution of the cumulative rainfall, there is the normal year, there is the El Nino year, which accumulates the deficits and gets larger than the non-El Nino drought here. So non-El Nino drought, because of this active period here, the deficits decrease and then it crashes. So the growth rates here are similar of the drought or the deficit, but in general the non-El Nino droughts are milder, less in terms of rainfall deficit. So the argument is similar in terms of the mid-latitude connection to the Arctic connection we talked about last year, to the last podcast, to the late season extreme wet events. So you have 200 millibar meridional winds and wind vector anomalies associated with this Rossby wave train. We had looked at southward and eastward. Here we are just looking mostly at the eastward at 200 hectopascal and 500 millibar hectopascal. And you can see that at the surface this has an anticyclone pattern both at 700 millibars and 850 millibars, which obviously is going to produce a deficit in rainfall. The region of action in the mid-latitudes is slightly different, so it is looking here at a lower latitude band. We looked at the Kara Sea before, which is up here. Are they related? I would say yes, because the Arctic Oscillation and the North Atlantic Oscillation have a high correlation and may have similar origins. The mechanisms for these are not completely accepted in terms of a consensus theory, whether the ocean is needed, whether it's a coupled mode, what selects the scales, and so on and so forth. Nonetheless, there is argued to be a cold sea surface temperature anomaly associated, which you would think will correspond to a increased Kara Sea sea ice extent and sea ice concentration, which would be the opposite of the one we saw before that was inducing wet anomalies. And they argue that associated with that are these vorticity anomalies in the atmosphere going from 700 to 200. So you can also integrate the vorticity anomalies and look at the relation with the sea surface temperature anomalies. So there is cyclonic vorticity anomalies associated with the sea surface temperature, which is counterintuitive. So in this case, probably the relation is not so direct, because cyclonic circulation tends to be associated with warmer SSTs if SST is forcing the atmosphere, whereas here it may be the other way. But it basically leaves that dynamic link not completely answered in this paper, but so mainly look for this mid-latitude link again. So it is somewhat consistent that there are wet anomalies being introduced by high latitude Rossby wave trains coming into the Indian region, which were related to the Kara Sea sea ice extent and the blocking pattern created over Western Europe and East Asia, and that steering the Rossby wave train down into the mid-latitude region, generating a divergence anomaly at the surface, creating a convergence anomaly at the divergence anomaly in the upper atmosphere, driving a cyclonic circulation and convergence anomaly at low latitudes, giving us late season wet events. Whereas here it's the other way, that there are cyclones being set up in the upper atmosphere, generating anticyclones at the surface, generating late season droughts. And this is good because El Nino droughts can only explain 50% of the 23 or so droughts that have occurred during the last century. And this seems to take the composite and give a explanation, a causal link to mid-latitude Rossby waves. So we didn't explain exactly if the wet and cold anomalies in the late season are the same process in opposite phase of Rossby waves, or whether there are slightly different processes involved for the origin of Rossby waves and their train making it into the Indian region. But it's good to have a good explanation for both late season extreme wet events and late season extreme droughts. Okay, we will leave it here.